by understanding the difference between a definite integral and an indefinite integral. What we have been working with in Chapter 4 to start with was the indefinite integral. And here's a big key point to recognize, that an indefinite integral is a function, or even a family of functions, where a definite integral that we had introduced in section 4.3 with the fundamental theorem of calculus is a number. So notice an indefinite integral is a function or family of functions. And by definition, what does the indefinite integral mean? If the indefinite integral of f of x dx is equal to capital F of x, so if when we integrate this function we get capital F of x, then what that means is if I took the derivative of this capital F of x, so if I took the derivative of the antiderivative, then I'm going to get the function back. And this is because we see the inverse relation between an antiderivative and a derivative. They undo each other in much the same way that addition and subtraction undo one another. Adding and subtracting are inverses. Multiplication and division each other. Multiplication and division are inverses, and so on. So the indefinite integral is defined as that function whose derivative would give us what we started with. But notice again that the indefinite produces a function. A definite integral has indices, so we're saying that we're going to integrate from x equals a to x equals b, and we're going to get a definite number. So notice this key difference. An indefinite integral is a function, a definite integral is a number. And that connection between them is what we pulled from the fundamental theorem of calculus. Look at some examples of some definite integrals. You should have this, you should be very familiar with this chart of definite integrals. Of indefinite integrals, I'm sorry. Let's make sure that you can see where some of these came from. So just a quick review of how, back in section 3.9, how we came up with some of these. If we were trying to find the most general antiderivative of 3x squared, if 3x squared is some value, that's we'll find what it is. But what we're looking for is what function can I take the derivative of and get 3x squared back? So how do I undo this, how do I undo the derivative out of this 3x squared? What we found was that to undo it, instead of decreasing this exponent, we're going to increase the exponent, and then we're going to divide by that exponent. So we'd get x cubed. Let's check that. If I do the derivative of this x cubed, I should get the function back. So in other words, if I do the derivative of x cubed, I should get 3x squared. And we can check and see, yes, the derivative of x cubed would be 3x squared. And so, yes, we can use we can use this method of checking by taking the derivative to verify that, yes, that is the antiderivative. Because it's an indefinite integral, we have to take into account that there's actually a family of functions. So I'm going to add a c, because there's an infinite number of functions whose derivative is 3x squared. For example, x cubed plus 1, the derivative is 3x squared. X cubed plus 2, the derivative is 3x squared. X cubed plus 7, the derivative is 3x squared. There's an infinite number of functions whose derivative is 3x squared. So I'm going to put the C in to account for that. I would need another piece of information about our function if I wanted to get one specific function. So back to this chart. This is in this same way how we can undo the derivative out of a function is how we would achieve this chart. But you'll want to be very familiar with this chart. Let's look at a few examples. So cosine of theta over sine squared theta. Ooh, you know, there's not a formula. There's not a answer to that up here in our table. There's, with regards to trig, there's only, we could find the antiderivative of cosine or of sine, but certainly nothing for sine squared or 1 over sine squared. So we're going to have to do a little bit of simplifying. And here's where you'll need to pull in some of your prior knowledge of trigonometry. And it's almost like a fun puzzle because we're looking at how can I manipulate this expression to make it look like one of these. I'm going for a sine squared, a secant tangent, a cosine, cosecant squared, or cosecant cotangent. And you might have already noticed it, that what we can do is we could rewrite it as a cosine over sine, and then a 1 over sine. And sure enough, this cosine over sine is going to give us cotangent. And 1 over sine is going to give us cosecant. And lo and behold, we have formula for cotangent times cosecant. It's the opposite of cosecant of theta plus that unknown constant. So notice for a trig example, sometimes you have to manipulate the expressions to get something on the chart. Let me say one more time what the goal was. We're trying to manipulate this cosine over sine squared to look like one of these 6 trig functions that we have a formula for. We could do something similar with this second example. As you look at this, you might notice, we don't have a quotient rule for antiderivatives, but we can simplify this. So I could simplify this into 3 separate expressions. Notice that this one's a definite integral. We're integrating from t equals 1 equals 9. But I can write this as the integral of 3 expressions over dt. And when I do that, I'm going to be able to simplify that to be t squared over t squared. So those t squareds divide out. I'm going to write that, for now, I'm going to write it as a t to the 2 minus 2 or 0. You don't have to write that with a 2, but going into the next step, I want to have that 0 there just to to make sure everyone follows what's going on here. For this next part, the t squared over t squared divides out, and we're left with a square root of t, or a t to the 1/2. And then I could write this minus 1 over t squared as minus 1 times t to the negative 2. And all of this is integrated over dt. So now it's just as simple as applying that exponent rule for integrating. over each of these three. The way I'm going to address this definite integral is I'm going to write the integration in a bracket. Then I'm going to have this vertical line saying that t is going to go from to 9. So 2t to the 0 is going to be 2t to the 0 plus 1, or 1 over 1, which I'm not going to bother writing because it's just multiplied by 1. T to the 1/2 plus 1 is going to be 3/2 over 3 times 2, because I'm going to divide by 3/2, so that's the same as multiplying by 2 and dividing by 3, minus t to the, now be really careful here, because -2 plus 1 is -1 over -1. And I could simplify this a little bit more. This subtracting a negative is going to change to adding. And that t to the -1 will be a 1 over t. Now what I want to do is integrate this from t equals 1 to t equals 9. Just a matter of doing some arithmetic. I'm going to start with t equals 9. Now 9 to the 3/2, the square root of 9 is 3, 3 cubed is 27. The way we work with definite integrals, we integrate for t equals 9. And then from that, we subtract the integration when t equals 1. So it'll look like this. 2 times 1 plus 2/3, 1 to the 3/2 plus 1 over 1. And now it's just a simple arithmetic, a 6th grade pre-algebra kind of arithmetic. And when you do this calculation, I think you should get 292 over 9 is approximately 32.4. But unless specified, you always want to give a precise and exact answer. Well, I hope that helps you get started with a basic understanding of the 4.4 topics. And if you do have some questions, I hope you'll bring them to class with you. I really want to highlight the importance of practice. For 4.4, I think that you'll find this work to get pretty easy. Some of you, hopefully all of you, will actually even enjoy doing this. It's just working out, almost like working out a number puzzle. But it will require you to put that time in with practice, and you will have a very difficult time moving to section 4.5, where we introduce substitute, if you don't fully understand 4.4. So please make time to do the necessary practice.